knowledge about binary numbers and binary number system in the Unix operating system. Okay, so let's start. So actually, a bit is the smallest unit of information on the computer. So it is either of a bit state of 1 or 0. And building on bits, the file storage is measured in bytes, and which is the smallest unit of storage. So here, the smallest unit of information in the computer is a bit, and the smallest unit of the storage is a byte, and 1 byte is equal to 8 bits. So basically, a bit is a number, either 0 or a 1. Okay. And a single character like a letter or digit or punctuation mark currently requires a byte of storage on the older computer system. And someday it might require 2 bytes on all systems, typical for advanced Unicode character. So a byte, which means 8 bits, and 1 byte can storage 1 byte can store a letter or a digit or a punctuation mark. And recall that a bit can only represent a single state of either being 1 or 0. So basically, a bit can only be one of 2 states. So computer needs to be able to represent all characters on the keyboard and account for the Unicode. And we use patterns of binary numbers to represent a typed character as bytes. So how many patterns of bits will we need? So basically, it will it will be 2 powered n patterns. So how many patterns for n? To conform the ASCII code, which has 127 characters, and Unicode, which has 128 characters. So totally, we need at least 255 patterns. And computer needs at least the minimum of 8 bits. So which we have 256 to at least 256 possibilities to use for the 255 patterns. And the characters are therefore assigned using a zero-based system to range from pattern 0 to 255. So the reason we need 8 bits here, you can see here is an example. So suppose we only have 1 bit and it will give you 2 states, like either 0 or 1. And if we have 2 bits and we can have 4 patterns here, like 0, 0, 0, 1, 1, 10, and 1, 1. So which means 4 equal to 2 power 2. And if we have 3 bits, and totally we will have 8 patterns. So suppose we want to represent 256 patterns. So totally we will need 8 bits. So which means because 2 powered 8 is equal to 256, and 256 can cover 255 patterns, and that is what we need. Okay. And to make sense of how the bits and bytes are utilized by computers, you need to understand the binary number system. So the decimal number system you're familiar with has 10 digits, like from 0 to 9. And the binary system has just 2 digits, 0 and 1. And it is possible to represent decimal numbers in the binary system. Starting from 0 are the first 8 numbers in the binary and decimals. For example, if you want to use binary numbers to represent 2 in the decimal, it should be written like 110, which means 2 in the decimal number system. Okay. And how to convert the binary number to the decimal number. So in the decimal number system, there is the ones place, the tens place, and the hundreds place going up by power of 10 and so on. In the binary number system, there is the ones place and the twos place, and 4th place and 8th place and so on, going up by power of 2. So read from the right to the left if you have a binary number like this. And you can see in the 1st place there is 1, and in the 2th place there's 0, and you can see in the 8th place there is 1, and in the 15th place there is 1. So if you want to convert this binary number to the decimal number, here is the formula, such as you can read from the right to the left, and the first position is 1, so 1 times 2 powered 0. Okay, and because this is the first position, so which represents 2 powered 0. So 2 powered 0 means 1, right? And from right to the left, and the second position is 0, so we will add 0 times 2 powered by 1, because this is the second position, and the position number is 1, and here we put zeros in the position, so 0 times 2 powered by 1. Okay, and at the third position, which is also 0 here, so 0 times 2 powered 2. Okay, and keep going. We have 1 in the 4th position, and 1 times 2 powered by 3. Okay, so basically this there the 0 here means this is the first position, so the positions index minus 1. Okay, because this is the first, so 1 minus first, it should be 0. And in the second position, we use 2 minus 1, so we put 1 here. And in the third position, we use 3 minus 1, so we put 2 here. Okay, and in the last position, we have 1 and times 2 powered by 4. Okay, so totally we have 25 here. Okay, so which means this binary numbers represent 25 in the decimal numbers system. Okay, so here is another example, just like I did. Suppose we have the binary number, which is 101101, and how to convert this binary number to the decimal number. So here is the formula. We can see from the right to the left, the first position is 1 times 2 powered by 0, because this is first position, so the index number here should be 1 minus 1. Okay, should be 0. And the second position is we put 0 here, so it's 0 times 2 powered by 1. The reason we use 1 here, because this is the second position, so 2 minus 1. Okay, and here is the third position's number, which is 1, so 1 times 2 powered by 2. So this position's index is 3 minus 1. Okay, this is the third position, so here we put 2 here. Okay, so keep going. We totally add these numbers together, and we got 45. And 45 is the representation of these binary numbers in the decimal number system. Okay. And the binary additions use the same principles as decimal addition, but with binary digits. So suppose we try to add two numbers together in the decimal system. In the decimal system, we use the carry if the two numbers, their sum are larger than 10, right? If the sum are larger than 10, we need to we need to make a carry to the next position, right? So so in here it's like in the base 10, if the sum exceeds 9, and you perform a carry. And similarly in the binary number system, if the base in the base 2, if the sum exceeds 1, then you perform a carry. Okay. So here is an example. Like if we want to add 1 to the 1 in the binary operating system, in the binary number system. So in the 1-bit place, 1 plus 1 equal to 1, 0. However, we cannot, I mean, actually 1 plus 1 means 2, but 2 exceeds 1, right? So you need to perform a carry. So which means you leave the 0 here, and this 1 is a carry position, okay? So the 1 of the 1, 0 is carried to the next bit place, as shown in here, okay? And the addition in the next place is 1 plus the carry number, this one. So it's also 1, 0. So you need to perform a carry to the next position, which is 1. And there is a 0 here, so 1 plus 0 is 1. So the sum of 1, 1, and 1 is equal to 1, 0, 0. Okay. And actually you can you can uh, uh, test the result of this sum by the decimal number system. So for example, because 1 and 1 in the binary number, actually it is equal to 3 in the decimal number system, right? 1, 1. And this one in the decimal number system is represent 1. So 3 plus 1 is equal to 4, and 1, 0, 0 represented as a binary number actually means 4 in the decimal number system. Okay, so in the decimal number system, 3 plus 1 is equal to 4, and which can be a validation of our computation process in this situation. Okay. So using the binary addition table, you can adding together binary numbers like the 3 binary numbers value of 1, like 1 plus 1 plus 1 is equal to, like, you first compute 1 plus 1, which means which equals to 1, 0, and add 1 to the 1, 0, which is 1, 1 in the binary number system. And this precise which is equal to the decimal number value 1, 1. So basically it's like 1 times 2 powered by 1 and 1 times 2 powered by 0. So which means it is equal to 3. I mean, you can convert this binary number 1, 1 to 3 by this formula. So it's like a test of our computational process in the binary number system, right? And here is another more complex example of the adding in the binary numbers. Okay, it's like if you want to compute the sum of binary number 111 and 11, so the result will be 1010, and here is the computation process. It's the adding table. Okay. And to convert the decimal number to the binary number, you need to make use of the remainder system. Okay, so suppose we already have a decimal number x, and the following step will give you the binary numbers of this x. Okay, so first you need to divide the x by 2, and for the first remainder, write it down as the first bit. leaving room to its left for more bits. Otherwise, write the remainder left over to the immediate left of the previous remainder. And if the quotient is not 0, replace x by the quotient and go back to step 1. Otherwise, move to step 4 to the next step. The binary number is the sequence of remainder read in order from left to the right. So here is the example. If you want to convert the decimal value 53 to the binary number, for example, first you divide the 53 by 2, so which means you will get 26, and remaining the remainder is 1, and this quotient is 26, and then you divide the quotient by 2 again, and you will get 13, and you will have the remainder is 0, and get the quotient is 13, and then you divide the quotient by 2 again, and you get 6, and remainder is 1, and divide the 6 by 2, and you will get 3, and remainder is 0, and divide 3 by 2, get 1, remainder 1, and you divide 1 by 2, get remainder is 0, and get quotient is 0, and remainder is 1. So here is you write down the remainder 1 and 0, 1. Make sure that every time you add a remainder here, you need to make this remainder on the leftmost. Like here is 1, and the new remainder is 0, so you put 0 on the left, and the right is the previous remainder, and the new remainder comes, you put it on the left, and 1 0 1, and here 0, so 0 1 0 1, and 1, and another 1 here, so totally you will get the list of all the remainders. So it should be 0, it should be 1 1 0 1 0 1. Okay. So make sure that this list is all the remainders. So for example, you cannot put the last quotient here, although it may be 0, but you cannot put it in here. Like you always put the remainders to this list, okay? And the final result will be the decimal number, which can represent this. This list will be the binary numbers, which can represent the decimal numbers 53. Okay. And if you want to test to check the correction, you can convert these binary numbers to the decimal numbers and see if it will equal to the 53. Okay. So here is the process of convert the binary number to the decimal number. Okay. And here is another method which can convert the decimal numbers to the binary numbers. And you guys can read the slides because for myself, I prefer the previous one, this remainder method. But if you're interested, you can still read this slide and study after the class, okay? And here is the example of this subtraction method.